Okay, so as I was saying, today let us just briefly discuss the concept of peak to total ratio. So what is it? It is basically another but yet very important way of what? Understanding the quality of the spectrum. Okay, we have already discussed this thing. We have written this down in your classes and all that. So suppose this is the spectrum due to a monoenergetic gamma ray. What is this one? This is the full energy peak. This is the background. Here you don't see any escape peak, so this is basically contour background. Fine. Now look at this structure, peak to total ratio. We have got peak. What is peak? Full energy peak of the peak of interest. Here we have got only one peak. Here this one. So this is the counts due to this peak, divided by two things over here. Number one, background. What is this background? This is the background related to the monoenergetic source that we are using. Fine. So this is the background. Here, this is the background. But remember that this is not the only background out here. Why? Because this whole stuff is not in vacuum, not in outer space where there are no radioactive sources, whatever. This is in our lab, and we have got everything around here, starting from cosmic rays coming from outside the earth, starting again from the concrete on the wall, floor, ground itself. Even we are also radioactive, but it is not that much harmful. So apart from this, you will also see something more. Here, maybe some peaks you will also see, but they are all belong to the external background. That means background from sources apart from the monoenergetic source that we have considered. Okay, so this is basically the peak to total ratio. Good. Now what to do? This is what it is. But you see, when this is a very simple case, where we have got a single gamma ray source, monoenergetic source. But in a real life experiment, lots and lots of gamma rays are there. More than 500 or so. Right? In that case, the background will be immense. How? Just give you a very simple example. Suppose this is a target, this is the beam, and so a lot of gamma rays are being emitted. Here we have got two detectors, here we have got another detector, very good. But is this thing entirely happening in vacuum? No. What about the detector itself? They have got casings outside them. So these gamma rays, apart from entering the detector itself, some may enter the casing, some may enter the iron structure which are holding the detector itself, or the wall of the room itself, and from there some compound scattered gamma rays will enter. Okay, so you see, the more the number of source, the more scattering will be there. So more scattered gamma rays will be there. So this means that this, if we have more number of gamma rays, that means more number of sort of monoenergetic source, so the external background will also be very large because of the scatterings from the other structures. Fine, basic idea. Now, but this is what it is. So how to? Okay, next question. Will this be a problem? Of course this is a problem. I am considering a scenario where say more than 500 gamma rays are being emitted. Okay, and I want to catch all of them. And in that scenario, all the other scattered gamma rays, they are in nuisance. They are external background. Okay, so what do we want? We want to get rid of them. Now we are going to talk about some techniques. I have already talked about this in my previous video. Now I am going to talk about it, very basic, you can say. I will summarize those techniques. Along with that, I will also talk about some new techniques as well. So this is the overall stuff. Now let me rub this part. Good. So the first technique is this. Suppose we have got a gamma ray entering a detector. Now you see this part, this part which I have shaded, if there is a gamma ray which interacts with this, look into this structure. There is more chance that the scattering will be away from here. That means we will lose the gamma ray. And the very less chance that the scattered gamma ray after scattering from this part will enter the detector. Okay? Because of this part basically is a dead weight. If we keep this, we are basically inviting more compound scattered gamma rays. So we will get rid of this. And this first technique is known as tapering. So this is how detectors look. Tapering of gamma rays. Tapering of front side of detector. This is the first technique. Next, what we are going to do? So we have got this taper detector. Good. Now what? Now, see, I have already talked about the anti-coincidence technique. Right? Now I am going to see here, use some other detector which will keep our detector as much safe as possible from this external background. Now you will ask me, sir, why have you put this cover, sort of cover on the detector on this side? The thing is that the gamma ray or from the target is coming from here, right? Now this is our internal, this is the target, right? This is what we want to study, the de-exciting nuclei, right? Radioactive nuclei which de-excites. We want to study those nuclei. Now, whereas this external background, there may be anywhere around, which can be induced by this reaction or from cosmic gamma rays as well, right? So, there is a lot of chance that they are from the other part, not from this part. That's why, since this is the important part, we have put the cover on the other part. Now, how does this cover works? Remember, we are talking about gamma rays. So, what's the most principal way of energy absorption? Photoelectric effect, right? What is it proportional to? Z of the detector, thickness, density, all of this, density and Z. Okay, now so if I use a material which has got very high Z and density, then what? Then effectively whatever secondary gamma rays come in, they will be absorbed over here and they will not enter here, right? So this is basically the technique of number 2 technique, passive shielding. So this is the second technique, passive shielding. Now there are problems. Problem is, remember, the absorption of gamma rays, it is exponential. I is equal to I0 e to the power minus mu x. Exponential nature means the attenuation keeps on, right? It is never zero. Another artifact is whatever, you may use a very thick shield, but even so there will be gamma rays which will enter over here after somewhat scattering. Of course they will be reduced, but there will be gamma rays, okay, which will be entered, and that will be a nuisance. So how to get rid of this? So the third technique is active shielding. This is what I have taught you in the last class. What is active shielding? I am going to use the condition, this and this, I am going to put the two of them in anti-coincidence circuit. Okay, so the logic will be x into y bar, and this is the output, x into y bar. See, this is x and this is my y. So suppose I don't have any signal over here. I don't have any signal over here. What will be the output? 0, no signal. Again, no signal over here. I mean no full energy peak from this target, but I am seeing a scattered gamma ray from here. Right? What will be so this is the case. Look, what is this? This is again 0. Now, next case, suppose I am seeing a signal over here, and again I am seeing a signal over here. What does this mean?
0.
This means that this has somehow entered over here and then scattered back to the detector. This is also possible. But again in this case it will be 0. And this will be 1 only when we have got this case. Signal over here but no signal, and then this will be 1. Okay. So this is the logic for truth table for anti-coincidence circuit. And in this case, the detector and the shield entirely is known as Compton suppressed spectrometer, CSS. So this is technique number 3. Now, what's the technique number 4? The technique number 4 is physical segmentation. Of detectors. Now, what is that thing? Before I talk about this topic, let me just talk about this basic idea first. So, this is the taper detector, fine. Now, we are talking about gamma ray, and this is the target. Now, you must understand that this target, okay, beam has fallen in the target. Okay, suppose the beam comes from this direction. This is my target, and after the production of the radioactive nuclei as a result of the nuclear reaction, the target in most of the cases they will be moving, and when the target is moving, not the target but the radioactive nuclei which is produced as a result of the beam and target, it is moving, and during its movement it emits gamma rays. So what will happen to the gamma ray? Since the radioactive nuclei is moving, so the gamma ray will be Doppler broadened. Isn't it so? This is the basic idea. We know about Doppler broadening. Now what is the expression for Doppler broadening? I am going to write down the non-relativistic expression. Beta cos theta. Good, no problem. Now what is this theta? This theta is, suppose if this is the beam direction and this is the detector over here, the mean angle, then this is the theta. Something like this, okay? Basic idea. Now what's the problem? The problem here is like this. See, this E gamma, now if you do the derivative, d of E gamma, then you will see terms due to dE0, again you will see terms due to d beta, and you will see terms due to d theta. Just if you do the derivative of it. Now this thing, what is this? D theta. D theta means this opening angle of the detector itself. How much is this? So this is your d theta. So this means that if the detector opening angle is large, then the gamma ray will be Doppler broadened by a very large amount. And again, remember what we are talking about. We are talking about a nuclear reaction. More than 500 gamma rays are emitted, and worst possible case, even after using these 3 techniques, if the Doppler broadening is there, then we will never be able to identify the gamma ray. Okay, so now we cannot get rid of the Doppler broadening because the radioactive nuclei will move. Of course, we can use a thick backing so that the nuclei will stop, but even so, there will be a time where even before the stopping into the backing itself, the radioactive nuclei will be moving. So we will get Doppler broadened gamma rays. We cannot get rid of it, but we can minimize the effect of Doppler broadening. How? I am talking about this case here. Concentrate on this. So if I use a detector which has got small d theta, then what will happen? Then this will be lower. What is this? D of E gamma means the energy. As a result of Doppler broadening, what actually happens, if this is a peak, as a result of Doppler broadening, it will be broadened. This means that basically you can think of it, the energy resolution worsens. See, this dE gamma will be larger because of these individual contributions. This is the result of Doppler broadening. This is if there is no Doppler broadening. Try to understand. So, if I am going to use a very narrow, a detector whose opening angle is small, see over here everybody, if I use a detector whose opening angle is small, then what will happen? We will have little bit better scenario. Okay, fine. But if I use a detector with small opening angle, my efficiency will be lower. So how to get rid of it? How to solve this problem? The way out of this is the following. If we have got a detector over here, right? So the gamma ray is coming from here. Let us bring in another friendly detector, identical detector, near it. Now what will happen? The gamma ray which comes here, most of them will be absorbed, some will escape from here, from here, from here as well. Now the ones which will escape from here, they will enter this detector, right? And there is a possibility that they will be absorbed. Now previously, remember we talked about the anti-coincidence technique. Now this time what we will do the coincidence technique. What is this? Let me give an example. Suppose I have got a 1000 kV gamma ray. Consider a scenario where this 1000 kV here gets contour scattered after 600 kV is absorbed and here 400 kV is absorbed. Now, if I do the coincidence of these two, then it is possible, what will happen is that I will do the condition like this, both of them together, then we will be able to get back this 600 plus 400 kV. Yeah. Because if I put the coincidence condition, the signals will be added up. Whatever energy is deposited in each of them, they will be added up. And this is known as add-back mode of operation. And this physical segmentation of detector, this is basically the composite detector. Let me show you some of the examples how they look like. Now we can have again series and parallel combinations of composite detectors. Series combination. So we have got one detector over here, another detector at the back. This is gamma ray. Now you must be saying, sir, is this hypothetical or they do really exist? You can check over the internet. There is something called HHS spectrometer. High resolution spectrometer. Okay. This works like this. There are two detectors back to back. So this is the series combination of detectors. Only two elements. Two elements stacked detector basically. Next case, parallel combination. See, four detectors are together. Why I am calling parallel combination? Because here the gamma ray will enter from here and after that it is scattered in the lateral part, but here it will scatter in this part. So this is series combination, this is parallel combination. Now again you can look over in the Google and see, this is the Clover detector. So these are real manifestations of the series and parallel combination of detectors. They are both very simple examples of composite detectors. Okay. Now remember, here we are talking about orthogonal geometry, rectangular type, square type structures. Now we can also have non-orthogonal structures as well. Let me show you. So this is orthogonal structure. So non-orthogonal. Let me talk about hexagonal shape detectors. So here, this is one module. This is another. This is another. How many detectors are there? 7 detectors. This is known as cluster detector. This is also, you can look into the Google and check. This is yet another parallel combination of detector, cluster detector. Okay, and you see, this is, you can think of the cluster detector like this. This is the center. Outside we have got 6 detectors. Right now, if I put yet another ring of this hexagonal shape detector, we will get the spectrometer for integral satellite. Cluster detector is made up of 7 modules. SPI is made up of 19 modules. Again, if I put another ring of hexagonal modules together outside of it. Try to do this. Okay. And you can also check my other videos. Here I have already talked about the SPI module. So I have just shown you different examples of parallel detectors. Okay, so what's the next part? The next one is tracking. Tracking detectors. Now, what is a tracking detector? Now, the tracking detector is in a sense very boring. We have talked about so many techniques, right? Now, what I am going to do, basically, this is the target, gamma rays are coming. So, basically, tracking detector looks like this. A very basic detector, no shielding, nothing. You must be wondering, sir, what is happening? What is this? Where is this tapering? Where is the passive shielding? And all this stuff. No, you don't need that. Why? Because whatever will happen, suppose some gamma ray enters and then it exists, we are going to track it using algorithms. So basically, we know, we use all these techniques if we don't know where the gamma ray is going. But if we have a very sophisticated algorithm, we know that if the gamma ray comes from here, if this much amount of energy is deposited, okay, where is the next one going? Suppose I detect the next one, then I immediately understand that this is the event which has entered, which has been recorded, is a result of Compton scattered gamma ray. Get rid of it. Okay, so this is the tracking technique. Here we use very sophisticated algorithms to identify the origin of the gamma rays, the nature. Okay, so this is basically tracking. You can check internet, there are very sophisticated detectors like Agatha and Greta. They are one of the first. Again, there are many. You can check. Again, regarding the composite detectors, I have talked about Clover detector. You can check the INGA array, Indian National Gamma Array. It's in IUSC, New Delhi right now. Sometimes it is commissioned in VCC, Kolkata as well. It's a group of 24 or more Clover detectors together. Even I have worked over there when I was a PhD student and later as well. Okay, you can check this thing. This is there in India and we use this. This is still operational. We use this to do a lot of nuclear structure reaction studies. Okay. Now, that's not the end. Again, let me tell you. There are other techniques. Here, you see, we have used principally only the gamma detectors itself. Nothing else. Now, apart from that, there are few other techniques for improving the P to total ratio. Let me talk about it. Say this is the beam, right? And this is the target. Now, what do you think the beam is? Beam is basically some stable beam. Let me talk about stable beam. So some stable nuclei which are coming to Earth. Now they are coming in a vacuum situation, so there is a beam pipe. From there the stable nuclei are coming. What do you think about the structure of the stable nuclei? There is a thorough structure or few nuclei together they are coming, right? Now if instead of this continuous beam, this is the continuous beam, instead of the continuous beam, look Siddhant over here, this is important, the concept. I use a pulsed beam. So, the fourth technique you can say is the pulsed beam method. Fourth, no, it is sixth. Sixth method. Pulsed beam method. Now, what is the pulsed beam? Basically, this is a continuous beam. I am not going to use that. I am going to use a sort of, you can say, package. So, beam is coming like this. This is beam, after that there is some time, again next part of the beam, again some time, next part of the beam, some time. Now you must be wondering, sir, what is this happening, why are you doing this? What do we get? Look, what do we get? After this part interacts with the target, okay, lots of radioactive nuclei will be produced, right? And then what will happen? If this is continuous, they will keep on producing and producing and producing, and then the gamma rays will be getting. Now, remember, some of the gamma rays will be very high. Some of the beam also, they sometimes are not stopped on the target, but they fall on the beam dump. This is known as beam dump. And then they will fall. Now, when this target falls over here from the beam dump, lots of another radioactive nuclei will be produced. Gamma rays will be emitted from them, and they are basically a source of secondary background. Now we don't want that, right? Now the technique is the following. Suppose I put this beam over here, then there is a gap. In the gap, I don't observe anything, because in this gap, what will happen is that all the radioactive sources, whatever they are there, they will be emitting their own stuff, but the actual reaction will not happen. Okay, so we can compare these two cases as well. আরেকবার বলছি, আমি একবারে বিম ফেলবো আর একবারে ফেলবো না। এই দুটো কেস কনসিডার করলে আমি এগুলোকে আইডেন্টিফাই করতে পারবো। So if I consider two scenarios, when the beam is there, when the beam is on, so beam is on and beam is off. So if I consider the two cases, then I will be able to identify the secondary background source coming from beam dump, coming from elsewhere as well. And so again I will be using the coincidence condition to study this and get rid of the background. And getting rid of the background means the denominator decreases and peak to total ratio increases. Okay. So this is the pulse beam method. Another technique. Again, not necessarily the last one, but for you it is the last one. The use of ancillary detectors. Now you see, till now we have talked about the beam, target, right? And we have talked about reaction. But remember, this is basic nuclear reaction. Large number of nuclei, charged particle, neutral particle, gamma rays, they will all be emitted. So, charged particle, neutron, gamma, even cluster of the nuclei, they will be emitted. Right? Now, these charged particles, they in fact can help us. These neutron, they in fact can help us. Let me give you an example. Suppose, as a result of the reaction, there are this set of particles are created. Suppose there is this X plus Y, it forms a compound nucleus C star, and as a result, this certain nuclei are produced. Let me just consider 4 scenarios. Okay, number 1, A plus 2 proton plus, that's it, A star plus 2 protons. Next case, B star. Star means this is an excited nucleus. So this will predominantly now be excited by gamma rays. B star plus P plus 3N. Next, C star plus P 2P plus 2N. C star plus C star. Oh, no, let me then use some other. Yeah, D star. Okay, and the fourth one, let me use, say, E. (5N). Now, we say this is a 5N channel, this is a 2P2N channel. We say like this. This is a P3N channel, this is 2P channel. Now, you see, suppose we want to study this nucleus, A star. Okay. Now, we want to study, so we have used all these techniques, good, sophisticated techniques till here. Even pulse beam techniques. We have used all the 6 techniques over here. But remember, during our study in the spectrum, we will observe the gamma rays from these cases as well. They are all genuine cases. None of them are fake. None of them are from the secondary sources, right? We will be there. But don't you think if in the spectrum they are there, they will be complicating the spectrum? Let me give you an example. Suppose from this A star there is a gamma ray at 101 keV. Here there is another from 102. Here there is another from 100 keV. And the resolution is not that much good. So what will happen? We will not be able to identify. So if we put a coincidence on the 101 keV gamma ray, we will get contributions from these two. Understand? So this is the problem with gamma ray spectroscopy. The detectors has finite energy resolution. So even if we just use only the gamma detectors and coincidence techniques, in the final spectrum, the coincidence spectrum, there will be scenarios where such cases will be there because of the finite energy resolution. Now, if we use a charged particle and a neutron detector as well, and we put a condition that we must observe 2 protons. So, condition is observe minimum 2 protons. This is, if we do that, then we will observe this case and we will observe this case. So, we will observe this case as well? No. We will not observe this case, we will not observe this case. Fine? But remember, this is also there. So, let me put another coincidence condition. 1 coincidence, 2 condition. No neutrons. So if I put minimum 2 protons plus no neutron condition, then I will get rid of this as well, and only in the final spectrum A star will be there. So this is the advantage of using the ancillary detectors. Ancillary detector means detector which charge particle, neutron detectors, which will help us in identifying our nucleus of interest for gamma ray spectroscopy. Again, in this case of ancillary detectors, there is yet another very important detector, which is a recoil mass separator. Okay, there also mass, charge can be separated. It's also very important ancillary detector, you can say. Write it down. So neutron detector, charge particle detector, and recoil mass separator. So more or less I have summarized the 7 methods. So we have talked about 7 methods.
Sir?
7 methods of improving the peak to total ratio. Bolo. Ancillary means you can say secondary detector. This is my primary detector, gamma ray spectroscopy, gamma detectors. This is regarding the beam. So these 5 are regarding the gamma detector itself. This is regarding the beam itself. This is regarding the supporting detectors. So 7 techniques, and this is the supporting detector which takes care of the charged particles, the neutrons as well. Okay, so keep this in mind. This is very important.